Hi, everyone. Um, Welcome to the Common Lisp Study Group. I'm your host, Ron Vadum with Atlanta Functional Programming. Today, we're going to be beginning our discussion or our journey into reading Paradigms of Artificial Intelligence Programming's Case Studies in Common Lisp by Peter Norvig, a book that I've been wanting to cover ever since I actually started this group for a long time. But at the time that I wanted to cover it, I wasn't as familiar with a lot of stuff in Common Lisp as I am now. So 7 years later, I'm now I think at a point where I can actually do this some justice. But in order to kind of like give in and start beginning some of the discussions about paradigms of artificial intelligence programming and actually start covering some of the chapters, I thought it would be useful for us to do a brief review of where we are in our Lisp journey, at least for me, where we are in our Lisp journey. Primarily because if you look at the book itself and its contents, the first part of the book that Norvig covers is actually a review of the language. Now, a couple of folks on our Jitsi group that are we're discussing, they kind of wanted to know at least where this is because paradigms PAIP is such a canonical text and something that most people are aware of, but most people don't understand when it was actually published and kind of why some of the styles that were used in the algorithms that were in the examples in the book were different than what we would consider to be quote unquote modern Common Lisp. So I wanted to kind of set the stage today, at least prior to actually reading that book and its review of Common Lisp in first part, with a brief history of Common Lisp itself as a language. This is something that I did as a talk at the Atlanta Functional Programming meetup in person a while back, but haven't covered it actually on this stream, primarily due to the books that we were covering covered a good portion of this, but I thought it would be nice and useful for folks who are on the channel to understand the place where we are today, especially given some of the stuff that is coming out in the public domain and open source in guys with earlier Lisp dialects. So Lisp itself is a very old language and has a very intertwined history with the field of artificial intelligence. Um, the father of or inventor of Common Lisp, the late John McCarthy, could also be considered one of the fathers or one of the main fathers of the field of artificial intelligence. He was also kind of a prophet in some of the later fields that we take for granted today. But in the case of artificial intelligence, it was really the folks over at MIT, specifically the late John McCarthy, when he was at MIT, along with Marvin Minsky, to create the first CSAIL artificial intelligence laboratory there. And in '58, when he ended up doing some work, I think it was at Dartmouth, he ended up looking at a language called, believe it was information processing language, IPL, which gave him the kind of the foundations to actually end up creating the mathematical theory that Lisp is actually based off of, which is recursive function theory, and eventually created what he thought was a theoretical model for a language that could essentially process on Lisp elements, and he called it Lisp. It wasn't until I think a couple of years later, I think it is in '58 or 60, that one of his PhD students took that specification and actually created the first Lisp REPL. And that obviously spawned off a variance of research and active Lisp development and programming language development. One of the first ones is obviously, and you guys can look at the history of this Mac Lisp that was available by, I think it was the MIT folks that ended up creating the Mac Lisp things. And then there were variants that were commercial variants that were created, like Lisp was created by BBN, which is now Raytheon. They had their own Lisp dialect. There was the CMUCL dialect that was out. Sorry, the CMU dialect that was out of Carnegie Mellon. Um, and there was a couple of other ones that were rarely in active development, and various, you know, uh, libraries and extensions were being built on each one of these, uh, along with dialects that ended up being used to and tailored for specific applications in artificial intelligence, one of which was actually the field of symbolic computation, which most people don't realize is actually a sub area of AI, just mainly because its purpose was actually to allow one to write natural, mathematical equations and being able to solve mathematical equations based on the symbols that you provided, which in retrospect, if you think about it, it makes sense because since symbolic mathematics, especially equations like of the form, your standard um, quadratic equation, which looks something like this in Python, bx plus c equals 0. These are all going to be treated as symbols in terms of your symbolic computation solver, and its purpose is to actually go and create the roots of the equation without having any fundamental understanding of the actual variables and what they constitute, which is what we end up adding in terms of programming languages. So one other dialect that actually came out of this space is kind of the dialect that ended up being the basis for Maxima, which is one of the first symbolic computation tools that was created, and it actually spawned an entire um, industry of people creating different symbolic computational toolboxes and tools, not and applications that created different solvers that are different than the one that Maxima provided. Just a side note for folks who are interested in Maxima and symbolic computation, Maxima is open source. It is available on SourceForge. We won't cover the at least I haven't yet covered symbolic computation, at least with respect to Maxima yet. But if folks are interested in it, it is something that we could think about on presenting at some point. Um, so a lot of work between 58 and 70 was actually AI and Lisp kind of developing hand in hand with these different dialects that were being created. And in around the early 80s and the mid 80s, it became apparent that no single Lisp programmer can go from one dialect to any of the other dialects and actually become productive immediately from day one, without other than the few primitive operators that were built on top of Lisp 1.5, which was created early on in the history before these dialects kind of branched out. Um, and this includes also one of the more famous dialects that I forgot to mention here, which is Interlisp. And it had its own, and this Lisp dialect was actually created by the folks at Xerox PARC. Uh, and one of its most famous features was something called Do What I Mean, which allowed you to define your interfaces and UI experiences in such a way that, it actually somewhat accurately correct executed what you kind of wanted in a GUI-like fashion. Um, so in the 80s, when a lot of this has happened, DARPA came around and told the AI folks, look, it's cool that you guys are doing all this kind of great stuff in AI on top of Lisps and creating these great, fantastic applications, but it's kind of bull that we can't go from one dialect to another. There needs to be some level of interoperability, and thus spawned the efforts to actually go and unify all the Lisp dialects under one moniker, which they labeled as Common Lisp. Um, the first edition of Common Lisp that kind of came out wasn't actually standardized. It was a book that was published by scheme inventor and fellow Common Lisp enthusiast Guy Steele. Most of you probably know Guy Steele from probably his work on Java and later on Fortran, which was supposed to be a Fortran-like dialect that's written on the JVM. But he's also very famous amongst Lisp folks for creating Scheme, which is a one of the I think the first I would consider one of the few first functional programming languages. It's probably right up there with Miranda, that came out of the folks over at Glasgow. But he was very active in the Common Lisp efforts too from day one. He published Common Lisp as standard in 1984. it was an unofficial document that kind of went through its own pains and stuff. And this is around the time that standardization efforts ended up happening. A second edition came out in 1990, which is around the time that I believe Paradigms of Artificial Intelligence Programming was published. So that actually ended up taking essentially a lot of first edition stuff and then some stuff from second edition, but I don't believe uh, PAIP covers stuff with the use of, say, when it's appropriate to actually make something more object oriented than, say, functional oriented. So a lot of the stuff that you're going to see in PAIP is basically more writing functions and maintaining state through the use of closures rather than creating def class structures. And just giving you a heads up if you haven't actually jumped ahead on this. Common Lisp also got standardized around this time and became the final version, which was the NCCL, and that was in 1995. No, no, 94, I think it is when it was standardized. It was essentially the year before C++ got standardized. So C++ and Common Lisp at least kind of shared this kind of commonality of being standardized kind of at the same time. Um, there were other efforts in also to getting the Common Lisp standardized in Europe. There was still an ongoing special effort. So if you go and look at the dialect for Common Lisp versus the dialect that I think Europe was trying to standard, it was either EU Lisp or ISO Lisp, one of the two. Um, there are some small differences because they kind of tried to address a couple of things that Common Lisp didn't happen at the time. For more information on a lot of this kind of standard stuff, honestly, I would point you all to Peter Seibel's actual great podcast. I think there was a podcast episode where he sat down and actually talked about the standardization efforts in Common Lisp and what went down, all the nitty gritties of the anti-Lisp efforts, what they were doing in terms of the participating at the international scale and all this kind of stuff. So you would probably enjoy and get a kick out of that, and gives you a good exercise in how even in Lisp programming language standardizations, there's a lot of give and take and a lot of politics and compromises that have to be made. That is kind of, I think, an important thing that for folks coming into learning Common Lisp, and something I learned over the years about Common Lisp is that Common Lisp may not be the best, okay, in terms of some of the Lisps that are coming out more recently, like Clojure, Dylan, and all sorts of stuff. But it was a compromise of unifying 7 different dialects at the time that had fairly mature applications written on top of them, very mature libraries that were written on top of them. And it was the efforts of a lot of people that actually tried to combine those things into this new stage. Now, for those who might be thinking, well, that's great, but it's now 30 years, 40 years since the standard came out, why not create a new version of the standard? The same reasons that I was mentioning about a lot of these politics and compromises fall today just as much as they fall then. And it is important for us to actually recognize that what would be useful is something of an organic style standard proposal document that can then organically be adopted by all the compilers. And I think we have that in a couple of efforts, mainly in Common Lisp. There is something called and I know Lispers will get a kick out of this. It's called the CDR, or Common Document Repository, if I remember correctly, is the acronym here. CDR, for folks who are aware for Common Lisp, actually stands for, I think, Contents of Decrement Register, which is the first. Um, it was actually I think a thin wrapper around what ultimately was the instruction that's being run on the IBM 704, which was the first machine that implemented Lisp. Um, but now, when we're talking about CDR proposals, we're actually talking about stuff that's, I think it's in called the Common Document Repository. Um, this actually contains a lot of organic proposals for getting different Lisps sort of talking to each other. and having their different extensions become more standardized depending upon, if folks are willing to do it. One of the most recent ones that I think that actually really surprised me, and this was a few weeks ago when we were covering the transducers topic, was the notion of local nicknames. Before SBCL put this about 8 years ago or 7 years ago, they had this available. You could not use local nicknames in packages other than in SBCL. And so, but it became so useful that they created the CDR, posted it, and a lot of folks ended up implementing essentially the SBCL version in their respective ones. I think now all most of the most active Lisp REPLs out there that I'm aware of actually have support for this standard. And there are other ones that are out there. I wish, and if there are any Lisp maintainers out there listening, and I'll be more than happy to actually participate in such development. One thing that I think would be useful is to actually standardize on user extensible sequences, so we can actually have user extensible sequences outside of SBCL. Um, and if there's a way to get this happening, this would be great. Um, I don't know if it can happen, but it'll also enable a lot of other libraries to work, just out of the box rather than adding um, REPL specific extensions in each of the individual packages themselves. Are there questions on this brief history? Give me just a minute. So I just like spouted like 10 minutes. So I just need to get a quick drink here. Okay. So there's a couple things about Common Lisp itself that I wanted to kind of call out, at least with respect to PAIP. And again, this isn't going to be covering the first three chapter contents ad nauseum. Just a couple of things that I was kind of um, noticing um, that Norvig was calling out that I think it is important because we don't, when you do Common Lisp on a day-to-day basis or even, on a hobby basis like myself, um, a lot of stuff tend to be taken for granted. Uh, but when you're learning Common Lisp for the first time or reading a textbook like Paradigms of Artificial Intelligence Programming, it is something to be aware of when you are dealing with the uh, the output that's being printed in a lot of these books. And especially it gives you the ability then to recognize, oh, this is a historical consequence. I can replace this function with this function. And it'll do the same thing. And it'll allow you to be able to pick one or the other when you are looking through some of these codes and adopting them into your own use cases. One of the things is, and I keep forgetting about this, but I was going to play around with it anyway, is, and this is just for REPL interactions, and that is the notion of using print case to determine whether or not you are dealing with upcase variables or low case variables. This is something that I always forget that's around myself. So this isn't a a beat down a feature that most people are aware of. But to put things into perspective, print case is essentially how you configure your REPL to um, print out symbols. So if you normally do not touch this, okay, um, I'm just going to show you an example. Like if you like create, something like the following: a list of Jane Doe, what ends up getting printed out is everything getting capitalized like this. And the reason for this is because in print case, we have it set to upcase, okay? And this is because of a historical consequence. Again, all previous Lisp distributions, all previous Lisp REPLs always actually printed out your symbols in uppercase. You could you could change this configuration by just simply, doing a setf on print case to one of the following things. It either could be upcase, downcase, or capitalize. And I'll show you what this would look like in the other two because we already seen upcase. So now if we try and running this again, you'll end up seeing that, the output has changed. And if we go in and change this to say capitalize, it'll always keep I think the first character. Um, it will always do the first character like so. So even if you wrote this Jane Doe or you wrote it, I think lowercase like this, the the same output is going to be the same. It's going to be, yeah. It looks like I heard that there may have been a question. Hold on.
Yeah, is there an option to just leave it whatever case it is rather than uppercase or lowercase it or cap case it?
That's a configuration. I don't believe so, but the if you go look at the hyperspec, I think these are the only ones that are specified. So that might be something that is a useful feature that we could add. But as far as I know, I don't think that there is one. But I can always go and verify this. I
That's
think
interesting.
yeah,
What's the
upper
variable
lower
called again?
mixed. I think is the only one.
What's the parameter?
Print case.
Print case.
Yeah. And so it's interesting. I don't it does correct it in most cases as you see there to fit the same case that it's and there is one case where this actually does not uh work in, and that is if you want to leave it alone, if you want to actually say have a symbol that's a leave alone, I think you have to actually specify that symbol using pipes around it. This is like a user defined symbol, not a symbol that it recognizes. If you wrote something like this, yeah, it will not touch the symbol. Um, so this is that dough there is I think there's a thing called make symbol. This is the output of make symbol. So if I say dough like that, you'll see that it'll end up creating a symbol, an uninterned symbol with the pipes around it. So other questions? Okay. So the other thing that I was like kind of, and again, this is just really just a brief review of some interesting utilities that this book kind of reminded me on is what was that? It was, oh yeah, the list functions. So most people know about if you have a list, and let's go and let's create a list. You know what? Let me actually use my scratch buffer here in this case. Okay. Okay. Let's create our list of test list that has a person's name like John Q McCarthy. All right. I don't think Q is his middle initial. So folks looking this up, it's I'm just using it. Okay. But so when it comes to list manipulation functions, I remember that most people are aware of first, okay, which will give you the first element of the list, okay, and and rest, which will give you the rest of the list, okay. And this is usually the basis for a lot of list manipulation functions nowadays. Although historically, for again, the historical folks out there, the first and rest is actually replacements for car and coulter. Car and coulter basically does the same thing. So if we do this using car and coulter, you could see that this is, sorry, car, not AR, car and coulter. You'll get the same, sorry, there we go. That's what I want to do. You'll see that you will get the same output. But just like there is, all these different variations on car and coulter up to I think 4 levels. There is cater, which is CADR, which is the first of the last list. So if I switch this to um, first of the last list here, we'll end up getting Q because naturally the last list is Decatur, which is Q and McCarthy, and then the car of that is going to be this. And then there's all the other variations that are available. I won't go and list them all here. Similarly, there's actually an equivalent functions for list manipulation um, that you can use too as well. On the other side, there are common functions I think that map up to like the same one. So there is uh, a um, sorry, a second and a third that you could then use, and then there's a fourth I believe too as well. So if you call this as a second option and you run this, you end up getting the same thing as you saw as a catter. And then if you do third, you'll see that it's going to be the same thing as before with the other things as well. So this is something that may not necessarily be useful now when you are actually going through some of your lists, but it is something that I do want to recognize and I do want to call out again, because I think I may have called this out at some point like, in the past, for folks who are just getting into Lisp and just joining us. Looking at some of these list manipulation functions that I forgot that was available at your disposal. Um, the third thing that I wanted to mention is not length. Length I've already covered before. We've already done that. Defining new functions, I think we've already covered ad nauseum. Okay, so one thing about functions definitions I think is important for most people to recognize. The documentation string that you provide in a function is the documentation string that spits out when you use the documentation function in your REPL. Okay, so when you're designing APIs, especially, I think this is very useful. I wish more people, I think a lot of newer libraries do this, but older libraries need to be somewhat updated. But if you're providing an external function, so that is a function inside of a package that is exported, okay? And let's say that this is our function foo, okay? And all foo is just going to return a string. You can add after the argument list a quick description of what this function is doing. So in this case, it's going to return a dummy string, okay? Um, and just returns this, okay? So what's useful about this is if you go now to your REPL here and you run foo function, it will go and look up the string in the symbols table. Sorry, the symbol in the symbols table, and then spit out the actual associated string. And this is very useful for those of us who are actually exploring an API via the REPL instead of reading documentation directly inside of the web. Okay, I understand that that it's limiting in some cases when you're writing some of this stuff, but it is very useful when you are writing out these libraries to have these little doc strings. There are actual, I think, efforts to make uh, a doc. There were actually early on efforts to make a doc test like so a Python, the Python equivalent for doc test inside Common Lisp. I haven't seen anybody really use it in that respect, but you could write more complete documentation if you really wanted to directly into the documentation string and then be done with it. I rather you wouldn't, just because that does make source code navigation a little bit of a pain. Like I know what you're doing when I'm looking at your code, but if you feel uh, that you wanted to add some more examples and things like this, and you think that it would be more useful to have it directly in the source rather than having a separate documentation string above the function code, go ahead. I just think it's a matter of preference, and I think that kind of documentation could be separated out into its own um, doc than actually being directly interleaved with the code. Depends on who you talk to. Some folks prefer one thing versus the other. Okay. Um, what else did I want to quickly cover here that I thought was pretty useful ahead of time? And again, if anybody has questions at this point, feel free to put them in the chat, and I will uh, address them in due time. Um, Okay, this is something I think that is important for us. So we've talked about higher order functions, and at least in the notion of mapcar and its ilk, there's a lot of different map functions that are available inside Common Lisp, and we kind of, at least I hope that I addressed in drove home the point that higher order functions, at least in terms of Common Lisp, is like a default way of writing good APIs and good code inside Common Lisp. Okay. Now, one thing that I would point out that I wish earlier codes in earlier books kind of pointed this out to me is yes, a higher order function does allow you to pass in an anonymous function has a, an argument, has a first argument. Okay. So to put things into perspective, like let's say that you are doing a simple map, okay, and I'm just going to use the map function because you could provide the return type here. Um, and we're just going to go ahead and then just run 1 plus on incrementing, let's say, I, sorry, for I up to 10, collecting I. Okay, so this code is fairly readable when you are writing your code, even writing up, say, the lambda version of this that takes in something, and let's say now we're printing out the squares, is also pretty readable too as well. But as soon as you start getting your lambda function to being like a half a page, which I have seen in some cases in production code, not just in Common Lisp but in other languages too as well, I think at that point you really need to think about putting a name to that function and then pulling it out. Now I understand that uh, in other languages that means you're creating a probably a static function that might be only be used in one place. But thanks to even stood function in C++ and its ilk, as well as function inside Java from Java util function, you have the ability to actually create these kinds of named functions above within the scope of the actual function body, and then you can call it in multiple places within that function body, and that has some advantages there that you can have. But in Common Lisp, you also have the FLET facility at your disposal. And this is something that I know we haven't really, like, I haven't brought it up a lot because there wasn't a lot of use cases where, FLET or even the let bindings other than variable bindings was important. But FLET does give you the ability to define functions. So if we wanted to say take the square function and make it into its own localized function within this particular form. We could simply just wrap this guy. Hold on. Dang it. That's not what I want to do. We could simply wrap this guy in a let form. Oops. Oh, my apologies. Looks like my I lost one of my key bindings. Shoot. Thank you. All right. Okay, where was I? Okay, we could just simply, sorry, not instead of using let, we use flet, and then what we could do here is we could just go ahead and define um, a function. Okay, let's say it's I think I have to put another set of parentheses here too as well. Well, let's see if this works. Square x and then do x. Okay, and then we could just simply do this here. Cut this guy out and hit square. And then this should actually work. Yeah, this is the same thing. So here, the flat now can clean up the code. And what's the advantages of this is if you have multiple places that you are writing out code and you wanted flat to kind of just like label the particular section of code, you could certainly do so. Now, in this case here, it's pretty obvious what this was doing. So the lambda function and the reading, both are kind of giving you the same effect of actually reading the code and cleaning it up. But I'm bringing this up because as you are doing at least some of the exercises in PAIP, this kind of cleanup will make your code much more readable than trying to use anonymous functions and ending up creating like massive amounts of anonymous functions um, inside of the scope of a particular piece of particular code and then make it almost unreadable. You have to essentially go back and doing the refactoring as a separate phase. Um, let's see here. Also, at this point, I think I'm going to bring up the fact that for folks who are out there who are seeing map for the first time here versus most of the time I end up leveraging map car. When you are dealing with lists, you could certainly leverage map car and it will be useful in some cases, but I will point out that MapCar will, I think, introduce a cons every time versus using map directly. So if you end up doing the same thing, and we could just simply run a time on this to see the difference on how much things are getting cons. We could do a time. Oh wait, what am I doing? Let me just grab this guy. Run that up. And here, instead of doing actually, let me do this instead. Let me print that. Let me do this here. Time map vector. We're going to do the same one, but we're going to end up creating about 1,000 elements for a more. At least I think it'll be enough for a decent demonstration on how much things get in cons versus what you would do with vector, because vector essentially does like an adjustable vector, so it'll have an adjustable fill pointer that will try and double the size of the array, much like most array lists or dynamic arrays that you know in other languages. And what I'll do is I'll just spit this guy out, and instead of doing this, I'm just now going to go map car, which now means I don't need to specify that. And By the way, map can also get the same problems with map car, because map you can also return a list if you need to, and some functions because of interoperability would end up returning lists versus returning functions. But knowing the difference is kind of useful. So if you run map car, ooh, what did I do here? Hold on, invalid arguments too. 1 second. Um, oh wait, sorry. I forgot to put a closing paren here. Okay. And let me just make sure. Okay. So if I run this guy, we could see that it's almost all in. Actually, it might be better to clear my REPL so I can put this side by side. So here is the results of map passing into a vector versus map car, which looks like, oh, I have the same problem. Ah, dang it. Let me do this again. I forgot that. Okay. Cost of me actually copying code without recognizing that I accidentally deleted a parentheses. uh, um, okay. Let's do this one more time. Good. Okay. So if you look at the difference between, let me scroll this up here a little so I can give you some space. In the map to a vector case, we don't even touch consing. It's a cons-free algorithm almost, right? It and although it looks like it's not, it's just that it's consing a large enough a contiguous block of memory up front. It's doing an alloc like you would normally do in a vector versus using a cons. And when we're designing algorithms for, say, some of the planning algorithms that are out there that are available in that book, as well as talking about some of the notions of phase generation and things, you will need to think about these kinds of techniques. Now, PAIP has some techniques, some known techniques that a lot of libraries have adopted for avoiding garbage collection, and it does actually talk about this in more detail. I want to bring this up front just mainly because of the fact that we have talked about a lot of libraries that actually does a lot of these kinds of tweaks and tries to emphasize more of a higher level style of programming without having to incur this sort of consing um, overhead because you will accidentally ended up creating a list of something rather than leveraging vector wherever possible. So this kind of benchmarking and this kind of like performance analysis is something that you may want to start becoming more and more aware of as you are actually going through some of the algorithms that we're going to do in these case studies. Um, what is the final thing I wanted to cover? Um, the last thing I really wanted to cover is was not append. Um, okay. When we Since we're about to embark on AI, and a lot of AI applications also, at least in the common Lisp sense, would probably do deal with some level of parsing and interacting with the Lisp REPL. I think it's important for us to actually at least be aware of how Lisp evaluates a particular S expression. So we know that we have a a read eval print loop. Okay, but what does the read actually do is something that's important to know. Okay, so and how does when eval gets called, how does it know what we are dealing with? Okay, and I think that's important to be aware of. I'm going to try and summarize some of this here a little bit. We'll when we start digging into the book in more detail next week, it'll be useful to be aware of. Um, but um, very quickly. evaluation rules for Lisp is pretty simple. Lisp is when you do an eval, uh, and I guess I'll just go ahead and write these here so you could see them on the things. The first thing is every expression must be either a list or an atom. This is an obvious one that most people should be aware of. What is an atom? An atom is a symbol. It's an indivisible symbol that could represent a variable that's inside of a symbol table, something that's been bound to a value in the context of a let binding. Um, these are all examples of symbols. A function name is technically an atom when it's splitting a list apart into different values, right? Um, so when you pass in something into the Lisp REPL, if it's not of the form of open paren, close paren, it treats it as an atom, or it attempts to treat it as an atom. And if it can't find that atom inside of its symbol table, it will barf and it will give you some sort of exception saying, oh, blah, blah, blah is an undefined symbol. So you can see that since X isn't actually defined in our REPL, if I go and type in X, I'm going to end up getting a condition here that essentially tells me that X is unbound. Now, one of for better or for worse, I'm going to also point this out to new lispers that are joining in into our channel and is about to listen to this topic, or a reminder for existing lispers that have been watching us for a while. When you specify something at the read and it turns out that it spits out that the variable x is unbound or the variable symbol is unbound, um, what Lisp actually does is it technically interns that symbol. So that means that symbol is now available, has a symbol, but it's an unbound symbol. So that means that even though the object is there, since it's not set, you could simply just do a setf x and it shouldn't barf anymore. All right. Um, So it now looks it up and actually is able to see this. Okay. The only thing it does tell you is that it's an undefined variable. It doesn't recognize that it's a variable. Now to actually properly unintern this, remember we do have the uninterned um, uh, function that will unintern this and remove that for this. So now if we do x again, it should spit out the same thing that we did earlier. It says x is now unbound, and so it reinterns it. Okay. Just to give you a little bit of a heads up. So lists or atoms. So well, what else is there? So every list needs to either be um, what's called a special form expression or a function application. Okay. Special form expressions are essentially stuff that we've covered before. Setf is a special form. Um, defun is technically a special form. Although it defines a new function. Quote is a special form. These are essentially forms that aren't defined as functions that are not in standard library. User-defined functions like foo are function applications. Okay, so when we're evaluating, we check if it's a Lisp or an atom. Is it a special form or function application? Is it a symbol or a non-symbol? Symbols we've already talked about. It'll go and look up that symbol, and if the symbol is undefined, it throws up a condition. Um, Symbols could anything that has earmuffs on it. Those are symbols. Earmuffs define global variables. Um, Things like this are important. But there's also one thing that's brought up, at least, um, and that Norvik brings up that I didn't realize was actually a technical term for it, but it makes sense if I think about it. Okay. There are also, so as I said, atoms are either symbol atoms or non-symbol atoms, right? But what are non-symbol atoms? Non-symbol atoms are basically atoms that evaluate to themselves. They're values essentially. Okay. So numbers, so like 42, if I type in 42 here in my REPL here, um, 42, um, without my REPL constantly to overwrite it. If I wrote 42 and evaluated it to it, that 42 is a non-symbol atom. Okay, the string hello is a non-symbol atom. Okay, the keyword argument, sorry, the keyword I think is also technically a non-symbol atom. So if I do, um, sorry, if I do not keyword, if I do uninterned like this is a non-symbol atom. Oh, hold on. Okay. Oh, it's uninterned, so it will actually spit out something is unbound. Of course, it's unbound. It's not. It's uninterned. Um, all these non-symbol atoms, and values are actually important to be aware of, just mainly because of the fact that when you are dealing with values, they are knowing that they're technically labeled as atoms internally by the Lisp evaluator will give you kind of a notion of what Lisp is registering as a value type. Okay. Um, Reading and evaluating, we've already kind of covered this in terms of how it does it. Goes, we have a scanner, we have read car, which is taking in each a thing that's happening in the evaluator, and it parses the expression, and then if it hits a function application, it'll go and call the function, and it will then keep on evaluating the expressions inside of a table until it completes the actual expression itself. One thing to be aware of is if the first element of the list, okay, is a function call, okay, say like in this case, plus 1, 2. It will, what it does is, what Lisp does is it'll check to see if the arguments are also themselves expressions. And if they're not, it'll then continue the evaluation. But if they are, it'll recursively go through and make sure that all the expression sub-expressions in the expression tree are evaluated. So in this case here, the children here, the expression 2 times 2 and the expression 3 times 2 will get evaluated first before it actually goes and calls the evaluation rule for the plus. In this respect, Lisp is an eagerly evaluated um, uh, language, and understanding this read and evaluation, especially when we start getting into some of the uh, case studies on, say, symbolic computation stuff and natural language processing, and leveraging parsing in the parse table wherever appropriate will become important. Now, I'm going to leave you guys here because I know this is a relatively short overview, but we're going to cover more about this in the coming weeks with a brief just a brief thing that we've kind of already covered that may become very important as we go through these case studies. A lot of these case studies at the time built their own sublanguages, heavily used made macros and so forth. But at the time, they didn't have this ability to, like, have different parsers being available at their disposal, like named read tables. We saw an example of this when we were covering our Neo4j series, where we needed to create a custom parser to take Cypher and convert it into an S expression. A lot of that will come and become tools at our disposal as we are going through this book. Um, I will try, where appropriate, to modernize some of the code without actually uh, diluting, if not making the concept more complicated. Um, I want people to ask questions. Please ask questions wherever appropriate, because this is material that we're going to be covering where we're using the book as a basis, but we're not covering it page for page, word for word. We might actually expand on what the book provides. Okay, so For those of you who are coming in expecting a full detailed overview of the book and it going chapter by chapter, that is not my intention with this book because again, this book and its problems is to explore artificial intelligence, all right, and to push the boundaries of our understanding on how common Lisp work. This is one of the reasons why I wanted to cover this book on this stream, and I encourage folks to have lively discussions on each of our videos as in the coming weeks, so that we can actually see what stuff is in this book that's useful for today, especially in the space of natural language processing and phase-based grammars where appropriate. So it might be in some situations where one might be exposing or deploying, say, an LLM where a phase-based grammar that uses a simple uh, what's it? A simple CFG representing a sentence structure is good enough. All right, and the cost of doing the LLM may not be a even long-term useful. So these kinds of things is something that only when you know what's available out there and only know when you know conceptually what these techniques are will you actually make informed decisions on what would be useful for your particular use case. So with that, I'm going to end today's episode. Are there any questions or misunderstandings or comments moving forward? Um, let's see. Okay. No questions on the stream. Judd, do you have any comments to point out? All right. Well, with that, welcome to Paradigms of Artificial Intelligence Programming Case Studies in Common Lisp. We will cover briefly Chapter 2 and 3 next week. I'm skipping Chapter 1 because I think I more or less covered Chapter 1 today without realizing it. And uh, we will try and start chapter 4 hopefully because chapter 2 and 3 is just again a really quick review on a couple of other topics related to common lisp that I didn't get a chance to actually cover today, just mainly because I didn't get a chance to actually read what he actually wanted to do, couldn't get a chance to expand on it. But the goal is to cover chapters 2 through 4 next week and then maybe um, move forward with that. So with that excuse me. With that, I hope you guys all enjoy your Saturday. Just a reminder, if you like our content, please like or subscribe to our channel. Folks who are not already registered for our meetup, please feel free to join Atlanta Functional Programming in our meetup. We are looking for speakers, so folks who are interested in providing topics, um, feel free to reach out to me. I'm available both on Functional Programming Slack as well as the Lisp Discord server, and I'm also available on Tech 404 for those who are in the Atlanta area. So with that, thank you for your time. Have a great Saturday. Peace.